In this question, we are asked to write down the time-dependent wave function for a free particle. So we're dealing with a free particle of energy E. And we need to find out the time-dependent wave function. So before I get into any of this, I'm actually going to derive the time-independent wave function, and then I'm going to write the time-dependent wave function. The answer is extremely simple, but the reason I want to derive the time-independent wave function is because in the book, the derivation is not given. It's pretty similar to solving any differential equation, any second-order differential equation. So I guess that's the reason the solution is not explicitly given, and thought it would be a good idea to actually derive it as a part of solving this problem. So the time-dependent Schrodinger equation can be written as IH bar times still psi over with respect to the derivative of psi with respect to time, and we have a second derivative with respect to the x coordinate. So this is a time-dependent Schrodinger equation. Now let's assume that the wave function can be written as a product of a function of time and a function of space, or the x coordinate, because we're dealing with one dimension here. So if I were to plug this in to that equation, I would end up, since we are taking a derivative with respect to t, psi of x is going to come out of that, and I don't have to use partial derivatives. I can actually use the full derivative. And here the derivative is with respect to x, so f of t is going to come out of that, and I can take a full derivative instead of a partial derivative. Now, what I'm going to do is I'm going to divide everything by the wave function. So I can cancel out psi of x, and here I can cancel out f of t, and here I can cancel out the entire thing. So this would give me okay. And here, in this case, we are dealing with a free particle, right? That would imply that the potential is zero everywhere. A free particle is basically a particle that's free of any external potential. So this is zero. Now, that would mean this would just this equation can be written as this, and we can completely ignore the potential because we're dealing with a free particle, and that's equal to zero. Now, the left-hand side is a function of time, and it's independent of x. Now, the right-hand side is a function of x, and it's independent of time. Now, we are telling that this part, which is a function of, which is independent of x, is equal to this, which is dependent on x. right? And we are also saying that this part, the right-hand side, which is independent of time, is equal to something that is dependent on time. Now, this can only be possible if these two are equal to a constant that is energy. So only in that scenario we can have something like this happen, right? So they should be equal to a constant which we call energy. Now, if we were to now we can solve these equations separately, right? So um, this can be solved separately, and this can be solved separately. So if we were to solve this, we can write this equation in terms of this. I can multiply and divide by I, and I squared is equal to -1. So I can write it as -1, but I can bring that -1 to the numerator. So it's gonna be this, okay? Now, what I'm gonna do is I'm going to integrate on both the sides. I'll be integrating with respect to time here, and on the other side, here I'll be integrating with respect to f of t. So this can be written as so this will be the integral, and we can then write f of t to be e to the power I e t over h bar. So this would be the function of time. I just want to point out that when we integrate it here, we would potentially end up with an integration constant. However, I did not consider that here because when we ultimately write psi of x, we can include the integration constant in this part. We can multiply f of t and psi of t by a factor, which could potentially incorporate the integration constant we see here. So that was the reason I didn't bother working with the integration constant. And this exact same thing is explained in chapter 1, where this equation is derived. Okay, so our goal here is to find out psi of x and t. And we found out what f of t is. We need to find out psi of x. So we can write this equation as to be equal to 2ne. I'm going to transfer the negative sign to the right-hand side. 2ne over h bar squared times psi of x. Now I can put all of these terms on one side of the equation to give me this. Now this is of the form of a second order differential equation. So we don't really have a term where we have first derivative of y or psi. We only have the second derivative of psi and the function psi itself. So we don't really see the the first derivative in this equation. And in general, a solution to an equation of this form is going to be something like this, e to the power sx. Now, if we plug that in here, if we plug this in here, we would get the second derivative would be s squared to the power sx plus now I can write it as under root -1, square root of -1 is I. So, I'm sorry, this should be a square root of the whole thing. So, yeah, and square root of h bar squared is just going to be h bar, right? So, s can be equal to plus or minus I times square root of 2me divided by h bar. Now, there are two possible solutions, one positive and one negative. So when we have two possible solutions that can satisfy a differential equation, a general solution can be written as a constant times e to the power one of the solutions times x plus another constant times e to the power the second solution times x. So in this case, y is nothing but psi of x, right? So we have found out the form of psi of x. Now we know what f of t is. We also know what psi of x is. So the total wave function, the time-dependent wave function, can be written as e to the power negative I e t over h bar times the time-independent wave function. So this would be the answer.